You are born inside a platform of sticks, not in a soft nest, not in a protected burrow, in a structure that weighs up to 900 pounds, built 100 feet above the ground, grown over decades of continuous use, like a factory that never shuts down. Not beside other chicks, not in safety, in direct competition with the sibling that hatched 24 hours before you. You weigh 3 ounces. Your sibling weighs 5. The math is already settled. While you are still trying to open your eyes that formed with 5 million photoreceptors per square millimeter, 3 times more than any human eye, your sibling is already eating. But that won't last, because at some point you will look at something 1.8 miles away, and you will need to make a decision in 0.3 seconds. And in that moment, every piece of engineering inside you will be put to the test. Advance 3 weeks. Your sibling is no longer in the nest. Not because it left, because you pushed it out, or because it simply stopped moving. No one records this. Your mother keeps feeding whoever remains. The stick platform stays. You have eyes that see in the ultraviolet spectrum. This is not a superpower. It is an engineering requirement. The rodents that make up 80% of your diet, mice, voles, hares, mark their territories with urine. That urine reflects ultraviolet light. To you, the field is not green and brown. The field is a map. Every rodent trail glows like a neon thread against the ground. Every concentration of markings is a traffic intersection. It is as if someone overlaid a live GPS system onto the terrain, with coordinates updating in real time, and only you have access to the screen. But seeing the target is not the hardest part. The hard part is the physics of what happens next. Your eyes process motion at 120 frames per second. The human eye processes 24. If you could see like an eagle for 10 seconds, most people would probably have a seizure. Question: do you think seeing faster would be an advantage, or would it be too overwhelming for the human brain to handle? Tell me in the comments. Skip forward. You are 8 weeks old. Your father lands in the nest with something dead between his talons. Not gently, not as a gift. He drops the carcass and leaves. You learn to eat alone or you don't eat. But what you are actually learning, without knowing it, is geometry. Every time you watch your father diving from altitude, you're watching applied differential calculus in real time. A red-tailed hawk, your close relative, can reach 150 miles per hour in a dive. That creates an immediate engineering problem. Air resists. The faster you fall, the harder it pushes back. Your body position has to actively compensate for that resistance, adjusting wings, tail, and angle of attack every 50 milliseconds. If your head were rigid like a human's in freefall, the wind would shake your vision. You would lose the target. But you have a fovea, a depression in the retina where photoreceptors concentrate, and you can move that fovea independently from the rest of the eye. While your body rotates and adjusts in the fall, your fovea keeps the target locked like a camera with active stabilization. You are not simply falling. You are a guided missile that no company ever manufactured. Advanced 6 months. You weighed 3 ounces. Now you weigh between 7 and 13 pounds, depending on sex. Females are 25% larger than males because they hunt larger prey. Your talons developed with keratin, as hard as metal, and a curvature engineered to penetrate between vertebrae. This is not accident. It is pressure geometry. The talons of a bald eagle can exert 400 pounds per square inch of force. For comparison, the bite force of an adult human is 160 pounds per square inch. You kill with your hands what a human cannot kill with its teeth. And the curve of your talons was optimized over 36 million years of selection, so that when they close, they require no conscious command to hold. Your talon closes by tendon reflex, like a trap. When you make contact, the mechanical system has already executed the capture before your brain processes that contact occurred. You do not think about gripping. You have simply already gripped. Skip forward. You are 2 years old. You hunted alone for the first time. A hare, 7 pounds, spotted at just over a mile away. The dive lasted 4 seconds. The impact was calculated for the base base of the skull. You eat on the ground, slowly, without urgency. It's the first moment the engineering inside you worked exactly as it was supposed to. It is not quite happiness. It is calibration, like a precision instrument finally tested under real conditions and returning the correct number. But there is a problem you have not discovered yet. Advance to the first breeding season. You are 5 years old. You found a mate. The stick platform you build together weighs 330 pounds in the first year. In 20 years, if you both survive, it will weigh 2,000. Every branch added is a piece of structural engineering. The freshest layers sit on top for insulation. The older layers compress underneath for support. But the problem is not the nest. The problem is that you need a territory of 30 square miles to feed a family. And humans have fragmented that territory. A power line does not look like a threat, but your wingspan is 7.5 feet. When you land on a utility tower and both wings touch different conductors at the same time, the current passes through you. There is no warning, no perceived pain. Just stop. In the United States, power lines are estimated to kill more than 10,000 eagles every year. 36 million years of engineering deleted in 0.01 seconds by a pole. Advance 20 years. You are still on the platform, but your bone density has dropped. Your talons still close with precision, but they take 0.04 seconds longer than before. For most predators, that difference would be invisible. For you, it means the hair that used to be catchable at 1.8 miles now needs to be within 1.2. You did not notice the shift, but your hunting success rate dropped from 45% to 31%. You will not die from an attack. You will die from an equation. The body will keep running until the margin of error reaches 0. And on that day, the dive will be perfect. The calculation will be correct, but the talon will arrive 0.06 seconds outside the window. And the hair will be 12 inches away when you hit the ground. And you will stay still. And you will try again. And you will miss again. Not because something broke. Because the system was optimized for the young. And you are no longer young. Somewhere on the same stick platform you built 20 years ago, a chick opens its eyes. It weighs 3 ounces. Its photoreceptors are still forming. The sibling beside it weighs more. The math is already settled. But at some point, it will look at something 1.8 miles away. And the engineering will begin again.